Ah, welcome to my research. Yeah, yeah. Ah, already finished. What the fuck? What the fuck? Uh, What the fuck? So, okay, this for navigation. Fuck. Fuck. Um, all that. Okay. Close the door. It's just a little bit of restriction. Oh, oh. But now I don't know. I'll do like when good.
Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem find minimum in a rotated sorted array. So we are given an input array of length n that is sorted in ascending order, but it could be rotated 1 to n times. For example, if we have an array like 1, 2, 0, 1, 2, right? To rotate it by 1 basically means to take the rightmost element, move it to the beginning like this, right? So this has been rotated by 1. We could also rotate it by 2 by taking the last two elements and moving them to the beginning. So something like this, right? This has been rotated by 2. And so we want to find the minimum value, and we want to do it in log n time, as they say. The good thing is that we do have some kind of sorting property that we can use to our advantage to find this log n time solution, and we are guaranteed that every value in the array happens to be unique. Of course, it would be easy to find a linear time solution, basically just scan through every single value in the array and then take the minimum value and return it, but we can use the sorting property to our advantage even if the array has been rotated. Let me show you how we can do that solution. As you might be able to guess, it is going to involve the binary search algorithm, which is usually the algorithm that runs in log n time. So the fact that the array was originally sorted is what hints to you that binary search might work in this case, but it's not going to be a traditional binary search. Now, of course, if the entire array was rotated n times, that basically means we took a sorted array such as 1, 2, 3, 4, 5, rotated it n times, basically leaving it in the original sorted order. Now, if we had an array that was completely sorted like this one, an easy binary search would work on a sorted array, but if the array is fully sorted, then we know that the minimum value is going to be the leftmost, right? So if at any point we get binary search is going to run like this, a left pointer and a right pointer. If we ever get to a point where the entire array is sorted, we can just return the leftmost element, or at least consider this as being the minimum value. So let's try a binary search and see how it's going to be different than a regular binary search. Now, of course, we want to find the minimum value. We're going to initialize our left pointer here and our right pointer here. Basically, the current pointer situation means that we are considering this entire array to find the minimum. The minimum could be from anywhere in this array. And the result is going to be the minimum, and I'm going to keep track of that over here. Now, of course, one way we could do this problem is basically find the pivot, right? Find the position where, the elements are not in increasing order, right? From here to here, 3 to 4, they're in increasing order. From 4 to 5, they are in increasing order. From 1 to 2, they're also in increasing order. But from 5 to 1, they're in decreasing order. This is the pivot, right? So basically, this value is going to be the minimum. But I'm going to do it in a slightly different way where we don't necessarily have to, look exactly for the pivot. I'm going to take, left, right, take the half of them, get our middle pointer. Our middle is going to be over here at 5. So I'm going to consider as 5 being the minimum value we have seen so far, right? So our result is going to be 5. Now we have to ask ourselves, okay, this could have been the result, but now we don't want to, look at this value again. So the question becomes, are we going to search to the left or are we going to search to the right? Where are we going to find the minimum value? Where are we going to find a value that's even smaller than 5? Well, first consider this. Since we rotated the array, we have 2 portions of the array that are sorted, right? We have this portion of the array that's sorted, the left portion, right? And we have the right sorted portion of the array, which is also sorted. So the question is for us, with this middle pointer, at this value 5, are we currently in the left sorted portion or are we currently in the right sorted portion? Now, if we are in the left sorted portion of the array, don't we want to search the right sorted portion? Reason being, if we rotated the array, the left portion is always going to have values that are greater than every value in the right sorted portion, right? Because when we rotate, right, suppose an array like this, we're taking the rightmost value, the largest value, and putting it over here, right? So we're taking larger values, putting them on the left side, right? So therefore, the values on the right are going to be smaller now. So that's why it's always going to be that way. So if our middle pointer is currently in a value that's in the left sorted portion, then we want to search the right sorted portion because it has smaller values in it, right? So how can we know if we are in the left sorted portion? Well, like I said, every value in the right sorted portion is going to be smaller than every value in the left sorted portion. So one thing we can check is if the current middle value is greater than or equal to the value all the way at the left of our thing, right? Because the left value is going to be the smallest value. If the middle value is greater than or equal to the leftmost value, that means this middle value is a part of this left sorted portion, right? In which case we want to search to the right. Now, if our middle pointer, suppose in this case we can see 5 is greater than or equal to 3. The reason we're doing greater than or equal is technically this middle pointer could actually be at the left position as well. That's one edge case. And in that case, we would also, this would be the left sorted portion. But suppose our middle pointer, instead of being at 5, was actually over here. It was at 1. What would our condition evaluate to then? Nums of middle would be 1. Is that greater than or equal to the left value, which is 3? It's not, right? Because the values in this right sorted portion are going to be smaller than the left sorted portion, in which case this would evaluate to false, right? If it's false, that means, if we're at a value that's in the right sorted portion, then we want to search to the left, right? Because in this case, the right, if our middle was at this, it makes sense that, okay, all the values to the right of it are going to be greater. So then we want to search to the left. But obviously these values are also greater, but that kind of doesn't illustrate the point, because what if our middle pointer was over here, right? Maybe we had some values over here. This is where our middle pointer is. We see 2. Okay. 2 could have been the minimum. Then we want to search to the left because we want to find even smaller values. Particularly, we would want to find this 1 that happens to be smaller because we don't know where the pivot is. The pivot could be here, the pivot could be here, it could be anywhere. We just know we have to look to the left if we want to find smaller elements. If our middle pointer happens to be in the right sorted portion, then we want to search to the left. If our middle pointer is in the left sorted portion, then we want to search to the right. And I just showed you the condition we can use to detect that. So now I'm going to run through the example and it'll probably make more sense. And by the way, the algorithm I'm describing only works on a rotated sorted array. If we ever got to a point where let's say our right pointer was over here, meaning that, this is our entire search range, then we could not do this algorithm. In this case, if we ever got to a portion of the array that's completely sorted, we would just take the leftmost value and see if it's smaller than our current result, and then we would stop the entire binary search. Okay, so now let's run through the example. These are the conditions that I talked about that we're going to be using. So our middle pointer is here. Let's check we checked that this might be the minimum. Now we're never going to look at this again. So now we're going to check, is this value greater than the value all the way to the left? Yes, it is. So we're going to search right. Since we're searching right, that means we're never going to search these values again. So we can cross them out. We're going to take our left pointer and shift it to mid plus 1. So our left pointer is now going to be over here. This is our new search range. And as you can see, this portion of the array is already in sorted order, right? How do we know that? Because the value at our right pointer is greater than the value at our left pointer. So that means that the array is entirely sorted, and then we can just take the leftmost value here, which is 1, see if it's smaller than our current result. Yes, it is. So then we can return 1 in this case. Now, just to kind of illustrate the opposite case, arbitrarily, I'm just going to say our middle pointer is actually going to be over here for some random reason. Let's just see how our binary search would work in that case. Well, we would take this middle value, say that it might be our result. So our result is going to initially be 1. And then we're going to run through these conditions. Is the middle value greater than or equal to the leftmost value? It's not. So we execute the else case, which basically means we're searching left, right? So we're going to take this is not going to be considered again. We're going to take our right pointer, set it to mid minus 1. So our right pointer is going to be over here. And we're going to cross out 2 because it's never going to be searched, right? Because we shifted our pointer. This is our new search range. Once again, you can see that this range is sorted. Basically, the left value is smaller than the right value. So this is already sorted. We can take the leftmost value over here, see, is this smaller than our current result? It's not, so our result stays the same, and we don't have to search this entire portion because it's already sorted. So that's kind of the general idea of how this algorithm is going to work. It's pretty easy once you kind of figure out these two conditions. With that being said, we can jump into the code. Okay, so now let's get into the code. As I mentioned, we are going to be maintaining a result. Now we can set this to some arbitrary default value. I'm just going to set it to nums of 0. We could just pick any value in the input array nums, but I'm just going to choose the leftmost just because. We're also going to have our 2 pointers. Initially, left is going to be all the way at the left at index 0. Right is going to be at the rightmost index, length of nums minus 1. And we're going to keep running our binary search while our pointers are in a valid position, while left is less than or equal to right. And like I mentioned, if we ever get to a subarray that's already sorted, basically if the value at the left is less than the value at the right, then we can update our result potentially, setting the result to the minimum of itself and the leftmost value of this sorted portion, and then we can break out of this while loop. If the array is not sorted, that's when we're actually going to be doing our binary search portion. So we can compute the mid pointer, basically left plus right, integer division by 2. And with this mid value, we're going to potentially update our result, setting the result equal to the minimum of itself and the value at the mid pointer. And once we're done with that, now we want to know, are we going to search to the left or are we going to search to the right? So how can we determine that? As I mentioned, the condition we want to know, is this mid value a part of the left sorted portion? It is a part of the left sorted portion if the value at the middle index is greater than or equal to the value all the way at the left. That means it is a part of the left sorted portion, in which case we want to search the right sorted portion. So we can take our mid pointer, take our left pointer, set it to mid plus 1. Now the else case is if we're in the right sorted portion, in which case we want to search to the left, so we set the right pointer equal to mid minus 1. And we're going to keep doing that until we find the solution, or until our binary search has basically searched the entire array, and then after that we can go ahead and return the result value. As you can see, this solution does run. It's pretty short and concise. I'm sure there are ways you can make it even shorter, but it runs pretty efficiently, so I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.